looser feel to it.
Yeah, it's got an almost improvisational tone.
This semester on Stat 201, prepare yourself for YouTube, because we're all zoomed out. Cahoots and special guests, Tiny Brian, Puppet Shark, Evil Moobot,
I am Moobot.
Morty the Rabbit, and more. Super Statistics Bros.
Hey everyone, how are we doing? Let me change. I feel like I changed the background back. We've got this background for a little bit now. Where's my backgrounds? Where's my background? I like the other background. Where's the original? Do a little. Words. Where is it? Smash effect. If anyone's in the chat, feel free to say hi. Organize this way better. 80s background. Oh, there it is. I think I found it. That means this is over it. Where is the background? Hey Savannah, good to see you here. If you got questions, let me know. My hair's being a little crazy today. If you have questions, we'll get started here. I'm trying to change the background back to what it was, and I can't find it. Trying to find it. Drop those questions in the chat. Wrong background. What's this background saying is showing, but the other one's new background. Okay, that's that. World news. Top 14 quiz. Yeah, which one on it? Sure. We'll use this one right here. I like maybe the green screen's all right. There we go. There's the green space. That's the one I wanted. Found it. Fixed it. So many things. There's so many buttons and things, but I couldn't find my other background. I'm pulling up MyPearson right now. Got my coffee. Went and got some Starbucks this morning. Went to the dentist. Nice shiny teeth. Which chapter 14 quiz? We did a little bit of it on office hours last time. We opened up Word down here. Microsoft Word. What should we do on chapter 14 quiz? Who's in place here? Chapter 14 quiz. Which questions? There's a lot of them. Grocery store shows receipts. Is that which chapter is that part? That's 14, right? We already done 13? So great job. Let's see here. Moving files. Okay, so let's get chapter 14 quiz on sampling distribution and sample mean. Here it is. Replace question. Oh. Now this is a tough quiz. I can't state this enough. Hopefully people hear these segments. But if you don't practice these, you're gonna have no idea what to do on the test. Like, you have to know the equations, you have to know sampling distribution, you got it. Found them, I think. Might be able to do that. Pretty much did all the 13. So have you done 13 already? Because I pretty much did them all during last office hours, so you probably saw the recording. And here we go, let's hop over to the main screen. So you might have done all those already. I'll look right over here. Nice, great job. The histogram to the right shows the annual compensation rates. Yeah, great job. Okay, let's put in the editor note. Okay, we have the notes up. We're looking for a grocery store, right? First store first. There's waiter, waitress. Famous question. Okay, so this one right here is the waiter, waitress question. Let me mark this and then make sure people hear it in the video. Okay, this is the same concepts. Okay, you got it. We'll do that one next. So here we are, marking it in the video. Stat 201, chapter 14, MyPearson quiz. and this is a grocery store. Okay, so Savannah, you know it. Get those points right here. We gotta wake up MewBot. He's not even in the chat yet. But what's the first thing we do when we get one of these questions? What is the very first thing we do? What is the very first thing we do? You know it. We say it all the time. We just, you have, people think your notation getting those points right here. MewBot is now awake, I think. So we say this to do notation. I think people forget. Did my points not go through? MewBot not listening to me. Let's hit the points button again right here. See if MewBot wakes up. But, and we also need MewBot here because I'm about to, ooh, is my point not working? Uh-oh, macro might not be working on points. We'll have to fix that because I updated that. Might have to do points manually from now on. Stream Deck's acting a little bit funny. We'll fix it later on. Fix it in post. Let me see here. Stream Deck. Stream Deck not awake? Okay, one more time. Okay. So with, there it goes. Had to reboot the Stream Deck too. So many things are broken. With this right here, notation is usually where people get stuck. And we're gonna take a screenshot of this and we're gonna start marking notation. Now, this is also gonna be on the Kahoot. The very first thing you do when you get to a problem, before marking notation, notation is one of the first things, you wanna figure out what kind of problem it is. Now, is this sampling distribution of the sample mean or sampling distribution of the sample proportion? Let's write step one up here. So this is the first step of solving this. Cat or quant, exactly, cat or quant. That's what we're saying, cat or quant. So if you're in, great job right there, Savannah. Cat or quant is the first step in amazing notes because this is cat, category, oops, see, I got it wrong. That is quant because the mean is quantitative. You can only get the mean with quantitative data. Quantitative, I say it that way for some reason. And proportions is categorical, like the proportion of people who own cats. So quantitative is proportions. And so you look at it and we're talking about a grocery store and how much the average sale is at the grocery store. So when we look at average sale at a grocery store, what are we talking about? Cat or quant? Which is means or, now you will find the mean for some of them, like what is the mean of the distribution of the sample proportion? That's where people get confused, and it's quant. So now we've identified that we're dealing with quantitative data right here because we're looking at the mean, what is expected over sampling distributions. So now the next step is mark your notation. And what I ask you to do is to go to the formula sheet and know it well. That's why we have review 2 already here. So print off your formula sheet now while practicing and basically pretend you're doing test questions because you're going to do test questions. So if you haven't already, go print off a formula sheet. Formula sheet can be found. Let me show you where it is. It's on the link that's pinned by MewBot right now. If you go to this page, you'll scroll down just a little bit and you'll see formula sheet. Nice job. Savannah's pretty much got it right there. And so it's already zoomed in to where I want it to be. We're going to grab this right here and Savannah has it. If you want to be more exact, Savannah, I think you have it, Savannah. There's a little more exact you can be because, and so great, Savannah, we're throwing you all the points. Just max out those points. The mean right here is mu. So this is mu. We found mu. And then the standard deviation of the distribution, it's down here, it goes across the screen. So there we go. The standard deviation is sigma. So, yep, and that's why now we found mu y bar. So Savannah's already said it here that we know mu y bar, the mean for the distribution of the sample proportion. That's what this says. The mean for the distribution of the sample proportion, mean, 100 points, Brian made a mistake. The mean for the distribution of the sample mean is equal to 33. And then the standard deviation for the distribution of the sample mean, standard deviation for the distribution of the sample mean, because the y bar is the sample mean, is equal to the original standard deviation over the square root of the sample size. And the sample size, well, we've already used that color, so let's not do that. The sample size is this. So marking your notation is key, knowing where to put in the numbers. And now we found a great job, Savannah. Savannah, I'm throwing you 500 points. You're just rocking and rolling right here with all the answers. I like that you're solving along with me. Let's throw you a big 500 points for a huge thank you. Amazing work. You came in here ready to do work. Let's keep just rocking through these questions. 1.296 is the standard deviation. So these two quantities are super important to find right here. We now know the mean, and we now know the standard deviation. We're just going to underline them here. This and this have been found, which means we can write normally distributed. So it's normally distributed with a mean of 33 and a standard deviation of 1.296. A lot of people forget to find the new standard deviation. This is the property that a lot of people forget to find when they're doing this. They just take the original standard deviation of 23 and plug that right here, but that's not what you're supposed to do for the distribution of the sample mean. Estimate the probability that the store's revenue will be at least $11,000. Well, if they have 315 customers, this is where this problem gets a little hard. If they have 315 customers and they want to make $11,000, then I'll just tell you, because we don't have too many task questions that do this, so I'm not so concerned. This is the sample mean they would have to get. 11,000 over 315. They'd have to get at least 34.92. So this is the super important quantity to find right here, which was the amount they want to get over the sample, which is on average they'd have to get 34.92. Does that make sense, Savannah, right there? Does that, are you following how I got that quantity? Because that's, you have to be able to find that quantity. It's going to be about, yep, good job. Amazing, amazing work, Savannah. I have a guess of it. It's going to be about that. And now what we're going to do is we're going to go to the applet to find the exact answer. So let's go to the applet right here, find the exact answer. You know how I got that guess? Just app or applet. I need to standardize the command. Is it exclamation applet? There we go. You both got it. I think I have exclamation applet and right there. So we need to take the standard deviation Savannah found, 1.296, and the mean of the distribution, which was 33. Both of these quantities are the quantities we found right here. We're just plugging in these two numbers and it's drawing the curve. These are the two numbers we're plugging in, found from the equations right here. The distribution of the sample mean has, or the distribution of sample mean has a mean of this, and the standard deviation of this. And now we're going to say, we want to see, will be at least this, so higher than 34.92. So above, and then you notice here, this is a probability, so we want to change it to find the probability using a value, 34.92, and ooh, did I? No way. Ah, I was so happy when I saw this. 6.92%, which would be, so we got close. You about just putting more things in the chat? So pretty good guess. It's about 7%. I was close enough, but I can't do that many decimals in my head trying to figure it out. Now it wants to know they service 315 customers. What about the worst 10% of days? So we've drawn what the curve looks like. So now if we think the worst 10%, is that on the left or the right side, Savannah? The worst 10%. The 34.92 came from, yep, and it is the bottom 10%. Yep. Yes, and you are correct, below the 10%, and then we'll see it visually. The 34.92 comes from, you have to take the 11,000, it's right here, this, what I'm highlighting right here for you. You have to take the 11,000 and find out what the sample mean would have to be. So you take the total and divide by the sample size right here. Yeah, no, please ask. That's where people get, stop me on any question. Where'd you get that? How'd you get that number? Because you're saying, it's like works this way. If I have to collect $100 from 20 people, I'd have to get on average how much from each person. So I have $100 I need to make. So if I were to need to make $100 and I had 20 people, on average they'd have to give me what each? Like you don't have to, you could get 100 from one person and be fine, but I have to at least get this on average from the 20 people to get $100. It's the same thing. Like if we want to make $11,000 off 315, it's the same idea. Like on average, you'd have to have at least this. Well, you wouldn't need at least 20 from each person. You'd need at least 5, because that way if the 20 people each give you 5 on average, you'd make 100. Does that make sense? 100 points right there. Don't worry. This is the concept of it. It's like let's say there's, you invite over, you and a friend are hanging out and you say, we're going to finish this 8 slices of pizza. On average, how many slices will each of you need to eat to finish the 8 slices of pizza? You and a friend are hanging out. There's 2 of you and there's 8 slices. So you'd say, well, we need to eat at least on average, yeah, so then 4 slices. So that's the mathematics we're doing right there. If you have 2 people trying to eat 8 slices of pizza, then they need to average at least 4 slices of pizza each to eat the 8 slices of pizza. Just trying to think about it like conceptually in other terms, what we're doing. We're just saying they want to make this much money off this many customers. They need to make on average this then. So the worst 10% of days, is going to be the bottom, the below, and then we enter in the percent right here. Now this is where people get confused because they're not going to make $31 total. This is what they make on average. Does that make sense? This is the average. So since this is what they make on average, we then need to multiply it by how many customers they are. So we take how much they made on average from the customers and multiply it by the amount of customers. So, and then Savannah has it right there. Great job, Savannah. And then we plug this in right here, round to 2 decimals, and we should be good. Yay! It's a good problem. It's a very good problem. Sometimes, I complain about the problems, but this is a very good problem. Very, very good problem. Should we do you want to do waiter waitress? It's the same concept. If we do waiter waitress next, it makes sense. Or we could do the other one you said. You pick, Savannah. You're here. You get to call it. You can say, nah, do the other one. Do the waiter waitress. The waiter waitress one we can probably do in not even 5 minutes, probably. We probably just do it super quick. And everyone wants to know, waiter waitress, how do you do the waiter waitress one? I'm like, not that bad. You know the steps. Each problem, you got to know the steps. Mark your notation. Find out if it's cat or quant. Yeah, thank you. Yeah, we got a lot. This one's a newer one. This one's like a reformulation of waiter waitress. It's only been around for the last year or so. So it's the waiter waitress one again though. So we could do that one later. Let's go do the other one you said about. And thank you, Savannah, so much. I like each semester I have like a person who usually like shows up, gets all their work done during office hours, and I really appreciate it. The histogram to the right shows the annual compensations. Let's do that one. Okay. Histogram to the right shows the annual compensations. Cool. Let's do it. And then we have a study. I'm going to pin this for now so I can remember it. I've got the other one pinned, you said. And really good work, Savannah, working ahead. I can't tell people enough that working ahead is the key, because then if you see something you're stuck on, like Savannah has right here, you can come in and ask your questions, and then you know exactly what you need to know, and you also know some steps that you've probably seen me practice. So really work ahead. And then when you're stuck, ask. Don't wait around, because if you're stuck and it's due, then you're stuck. If you're stuck and you got time, get stuck. Skew to the left. Oh yeah, we'll do the skew to the left one too here. The histogram to the right shows the annual compensation in thousands of dollars of CEOs of 800 companies. The average compensation in $1,000 is this. That's it's 8.5 million, I think. Yeah. Oh, I just don't. In that one. Oh, sure. Oh, is this a different one? I will do this one really quickly, and then we'll do the next one. I'll try to be quicker on this one then. And so then we are drawing samples of 30, 50, 100, and 200. So what this is going to do is this is going to be the central limit theorem right here. Central limit theorem says 2 things. That the distribution of the mean will get more normal and tighter as the sample size increases. So I think Savannah's pointing right now that the original distribution is right skewed, and because right to the high, left to the low, and we got to take a half second to draw our monster man, because one thing students never forget after my class, I've had students tell me afterwards, is they never forget how skew goes. I've had people say, wait, is it right or left skew? And then once you learn monster man, you never forget skew. I've never had problems with my students not knowing what skews because of monster man. Love the monster man. We got to draw him. We got to remember him. Always remember monster man, right to the high, left to low, whatever way the monster man's tail goes. If you come up with sing-songy ways to remember things, you remember them a lot better. That's something I've learned about education. Is singing it helps you remember it. Explain how these histograms of the simulated data show you this concept. Once again, write down the 2 things or know them on the central limit theorem. This is the original distribution. When it comes to the central limit theorem is not about the original data. The central limit theorem is about the distribution of the sample data and what happens to it as the sample size increases. So what we get right here, the applet, let me try one more time. Central limit. Here we go. So notice that this is a right skewed distribution. just like ours. But if you look at that, same sort of thing. Now, when you take a small sample size, like let's say of 2, the distribution of the sample mean is the average. Notice every blue dot is the average of the 2 black dots. So every blue dot down here, because this is the distribution of the means of sample size 2, is the average of 2 black dots. And if you notice what happens if we do this, it looks tighter, exactly, and more normal. And the mean will stay the same, and it's going to become more normal. Now let's increase n right here. Now this is the average of 10 dots. So all these 10 dots are being averaged to 1 blue dot. So every blue dot down there is a distribution of the mean of sample size 10. And look, it's even more tighter and more normal. Tighter means smaller standard deviation. You go up to 25. Now every blue dot is the average of 25 observations. And so now 1 blue dot is the average of 25, and it's even more tighter. Look how it's less spread, less standard deviation. And watch this, 6.25 divided by 5. 6.22 divided by 5 is 1.25, or rounds up basically. And if you keep the simulation up, it'll go to 1.24 probably. It'll eventually probably reach that. It's just so close, decimal differences. And that is the central limit theorem. I knew the answers to that or how it would go because the central limit theorem states what will happen. Just like in this problem here, you can see as sample size increases, it becomes tighter and more normal. Now, because this is so heavily skewed, it doesn't become perfectly normal. This is a weird one that I'm not the biggest fan of, because if it's super duper skewed, you need more than 100. So this one's super duper skewed. Like if it's skewed 25, if it's very skewed 100, and if it's super duper skewed, which we don't even put on the test, something like 500. It's just the more skewed it is, the larger n needs to be, which is the third condition for the distribution of the sample mean to be normal. Condition 1, random. Condition 2, less than 10% of the population is sampled. And condition 3, large enough n such that the distribution is normal. Read through the slides, check out my videos going over that. Let's answer these questions. The simulations do show, simulations will always show, because they show reality, what the central limit theorem states about the sampling distribution of the sample mean. As the sample size increases, the peak of the histogram, which is where the mean is at, stays the same. And the shape of the distribution becomes more normal. And the variability, which is the standard deviation, will decrease. That's the standard deviation decreasing. This is the mean staying the same, and that's it becoming more normal. Comment on the rule of thumb that 30 is always large enough. No. If it's normal, 1 is large enough. If it's skewed, 25 is large enough. If it's very skewed, 100 is large enough. If it's super duper skewed, you probably need 500 or 1,000, but that's not even on the test. That's more of an advanced concept. So since the distribution of the means for the simulation distribution becomes distribution of the means for the no. I think it's this one. The distribution of the means for the sampling distribution of any size remains skewed. Correct. So, oh, it's A. Oh, good question. So it's always going to become more normal, but sometimes it can be so skewed you need a very large sample size. The way they ask this, not a huge fan of it. I've spent 20 minutes talking about this one condition, and then I feel like students are more confused. Maybe I'm going to do one segment right here, and then we'll do the next question, because a lot of people wonder about this third condition. I'm going to put it in the video right here, and we'll try to do it in 3 to 5 minutes. And I'm going to tell you how to check it very concisely. Okay. How do we check the large enough n condition? I'm going to try to talk about it less after this, so we can just do a segment on it. Okay. Large enough n condition. Here is how you check it. The way you check it is step 1. What is the shape of the parent? What is the shape of it? And when it comes to the shape in our class, there'll be 3 shapes you can pick from. Normal, we'll say normal-ish, skewed, or very skewed. So these will be the shapes. Normal-ish, skewed, or very skewed. Step 2. Circle the required, or circle the shape. circle the required size related to the shape. Okay, so now it's not even a question because we're going to say here 1, 25, 100. Does this make sense, Savannah, right here? Like, I'm making a flow chart on how to do this. This isn't even a question because it's like, if you say your data is skewed, now you do this. So that's what I want people to do. Or if you say your data is very skewed, you do that. So whatever one you pick, it's like you pick the one below it. So that's like, you never do this. This is no. Don't do that. You circle the one directly below it. This is that right there. Okay, now we're gonna do a 4-step process. Usually I do this in 3, but I think the 4-step helps. So step 3, what is your sample size? Okay, and then step 4, if this is true, you are good. And then we'll put it here, step here. Okay, or we could just, we'll write in what these are. Only a step. Okay, so sample size greater than or equal to and we'll call this required. We'll do one example of this and see if we have it. Hope this flowchart really helps people. Call this required. And then okay. This is as probably as clear as I can make it right here on the steps to do. Is your sample size greater than the required size? Okay, so here we go. We're going to try an example of this, see if we get it. We'll do 2 really quick. So here is the shape of the original data. Okay, what's the shape of the original data? What is the shape of the original data? The shape of the original data is what? The original data is like what you're drawing from. It's normal. Okay, so what is the required sample size for normal data? Great work, Savannah. Good practice. What is the required sample size to meet the condition? This is, we're not saying we have this. We need at least 1. Okay, then what is, you have to look at the applet. What is my sample size? The question would state this. You have to look right here. What is the sample size I have? What's my sample size? 2. And is 2 greater than or equal to 1? Is 2 greater than or equal to 1? Is 2 greater than or equal to 1? So then, is this a fact that 2 is greater than or equal to 1? Yeah, no worries. Don't worry, you're practicing. This is and so then you've done it. So what this means is when I run the simulation, no, totally fine. Another more points in the chat. When I run this simulation right here, here's what happens. Guess what? This looks normal. But now let's do the opposite so you can kind of tell where we're going. What is the shape of this data right here? What is the shape of that data right there? What is the shape of that data? So that data, just remember what it looks like right there. What is the shape of that data? What is the shape of that data? We just had one that met it. Extremely skewed. So we're going to mark the very skewed over here. So what's the sample size we would need if it's very skewed? If it's very skewed, what sample size do we need? We've already said this data looks very super duper skewed. We need at least what? This is extreme. You just go right below it, just right below. We've got them in line. 100. And then our sample size is still 2. And then 2 greater than or equal to 100 is not true. So we don't meet it because we don't have at least that sample size. So you know what this means? When I, great job, Savannah, right there. When I run this test right here to see what it would look like as I lose my mouse for the millionth time. There it is. When I run the simulation, gosh, the simulation comes out with data that doesn't look normal. Look at that. Does that look normal to you? No. This is not normal data now because we didn't meet the conditions of, it might have been, it's randomly sampled, it's probably less than 10% of the population, but it's not a large enough n such that the distribution will be normal. And of course, as we increase, it becomes more normal, still skewed right here, but a larger n will make it more normal. You need a larger n when the distribution is more skewed. So the more skewed it is, the larger n needs to be. Check out this portion right here. I said 3 to 5 minutes, it was like 7 minutes. Let's do that next question. Savannah, thank you so much. I hope that helps people out a lot because that's usually the condition. People are like, wait, what does this mean? What is the large enough n condition? How does that work? But making it into steps, I think really helps people, like steps. It's this one right here, right? The CEO one. You wanted the CEO one, but there might have been another one. Annual compensation of CEOs. Tell me if there's another one, Savannah. But we're doing, this is one of the ones you mentioned. One, it starts out easy-ish. This one's tougher because the decimals a lot of times. We did skewed left version. Yep. Here we go right here. We'll do this one and then we'll do the last question. Yeah, sure. We'll do the skewed left. Is it like, did it just like permutate the version? I might have to like change versions. We'll do that here next because you mentioned this one too. So here we go with this one right here. Now, number one thing we do when doing these questions is we ask if it's cat or quant. Guess what I'm going to do though? I'm going to tell you which one it is. And this one is going to be quant. Well, one, because we're doing the chapter with quantitative. And we're talking about how much money do they make. So if you're wondering why do we say cat or quant, well, it's because the formulas we use are going to be either categorical or quantitative based. And are you dealing with sample means or are you dealing with sample proportions? That's what sample means are. Oh, nope, see, put them in reverse. The quantitative is the sample mean and the categorical is the sample proportion. So because this is compensation, compensation will be in dollars. And that's going to be quantitative right here. And then we would need to find the mean for the distribution of the sample mean, which is equal to the mean, and the standard deviation for the distribution of the sample mean, which is equal to the original standard deviation sigma over square root of n. Write down each one of these right here and practice them. When you say sigma, original standard deviation over square root of sample size, that's that formula I wrote right there. Know them, write them down. And I'm going to just copy paste from the formula sheet again because it's a lot clearer than my handwriting. But you want to be able to have your formula sheet beside you, print it off, just take a moment and print it off and be looking at it when you do the problems. It'll help prepare you for the test. So since we've identified we are doing the sample mean, ooh, nice job right there. Maybe, let's go see right here. Well, the first part of this question, the mean stays the same. That is correct. Savannah, you're basically there. So Savannah's kind of figured it out. The mean stays the same. So whatever it says the mean is, so it says the mean is this. Here's the mean and standard deviation. So this right here will be in all these boxes because this is simply mu y bar equals mu. That doesn't change. But now the next one is the standard deviation of the sample mean is equal to sigma over square root of n. Now n is going to change because n is the value right here. Yep. And this needs to change as we solve the equation. The standard deviation is going to be the value right here, and the standard deviation is going to be that. So each one of these, does that make sense, Savannah? Each one of these you have to plug in the original standard deviation of 19,012.18.82 divided by square root of 30, next time divided by square root of 50, next time divided by square root of 100, next time divided by square root of 200. So we just have to do a bunch of busy work basically. And it shows you as you do this that the mean stays the same. You can go right here and do 10, 6, 2, 2, 8, 1. And you can also see the simulations showing you what to expect, which is going to be basically, now you don't use the simulation numbers. We'll just get numbers that kind of show what the simulation shows. The standard deviation right here, we take the 19, or we do square root of 31st, because you have to then save this, copy it, and take 19,218.82, divide by, and then you got to do the next one here, and it's 50, which is like 7.07. That's a neat number. Mubot talking away in the chat. It's so easy to make a decimal error on these. Just copy paste a lot. Oh, we can do this one in our head. How'd you do this? Move decimals. So square root of 100 is 10. Divide by 10, move decimals. I take the well, not the mean. Am I taking, because this is the standard deviation right here. So we take the sample size of 200, square root, and that's the square root of 200 right here. No worries, no worries. And we take the standard deviation, sigma, and divide by, yes, exactly. Standard deviation divided by square root of n. Yep. And we should have this correct now. That rounds up. I'll go back to the sheet so you can see it again right here. There's the work right here on the sheet. I'll zoom in a little bit more so you can see it. And then the equations are down here where we're doing the standard deviation of y bar is equal to the original standard deviation over the square root of the sample size. So basically you just want to be looking at your formula sheet and plugging in the numbers. So the key thing is like grab this formula right here and then use it right here, then know where your other information is at in the problem, like the original standard deviation. So I've got it color-coded, highlighted, so we can kind of plug in the numbers. And then the mean is the mean, which when you're dealing with the mean, it's this data is this data right here, which is what right there. So just very important to know what you're dealing with each part of the problem. And then see the conceptual parts, like the mean stays the same, the standard deviation gets smaller. The values are pretty close. Simulations model it, they're reasonably close, and the other ones are reasonably close because simulation, cancel, I don't, there we go. It will basically model what we have. So you can kind of use these numbers to check your answers, kind of, not really. I mean, if they're really far off, then that's a problem. But notice 14,000, 14,000, 19,000, 19,000, 27,000, 2,700, 2,700, 3,400, 3,500. Little differences, and then the mean is always the same. But good stuff. And then we want to do the left skewed one. Does this one say left skewed at times? It's the histogram to the right shows. I think this one's always. Is it this one, Savannah? What's the, just past it? Is it this one? If you remember what question it is that I just clicked on, is it 5? Can you tell me which number it is, or was when I cycled through, did it show it in the different versions? It just has a very left skew. Which number do I need to click on? 4, 5, 6, 7, 8? No worries. Which number was it that I needed to click on? Like 4, 5, 6, 7, 8? This one has a little left skew. Is it this one? Is it this one right here? Because this one's right. There's Waiter Waitress. Is it on the homework maybe? I'll click through, and if you see it, just say question this. Salmon one's interesting. So few questions. Was it this one just showing different versions? Oh, there's left. So I think it's this one right here, right? If it's skewed to the left, I think it's just the same thing. Like it's the rule stays. Yeah. So if it's left skewed or right skewed, it's the same sort of concept. It's just it's weird. the data just becomes differently skewed. But no, it's the same concepts. Yeah, it's just a different, they're just trying to change it up and be like, so that way you can't always answer right skewed on these. That way, when you look at the problem too, you have to identify left or right skew. Yeah, no, good question right there. Yeah, it's just like, hopefully the student, if you think about what we want you to know, is we want you to be able to know skew. Because a lot of the concepts just go into additional chapters, which is really great. Like if you learn a little bit of Stat 201, it helps. I guess the Salmon one's kind of interesting. It so if you notice, it wants you to keep finding the standard deviation. Now here's the thing. Notice how this says SDY bar. What do you think you should look at if you're doing this problem and you see SDY bar? You would need to find two things now. So what two things would you need to find? If you want to find the standard deviation for the sample mean, that's what that says. The standard deviation for the sample mean. What two things would you need to find? The standard deviation for the sample mean. I need to mark this question. Almost didn't mark it. Well, you can find those. Not quite. Good answers. Keep going. I'm gonna mark the question right here. And 100 points. Keep up those answers. So. What two things do we need to find for this problem? We can find the things you said, though. Nothing wrong with that. Well, we can, yes, that is commonly what we do find. And this question, and so you're right, but the question wants us to find, the question keeps asking us repeatedly, what is SD, the standard deviation of the sample mean? It keeps asking that. So now what two things would we need to find those, to find that? So we look right here and we say, if we want to find this, we need to know what? You're on the right track. Usually we find the mean and the standard deviation of a distribution. Like, that is true. That's a fact. But if we want to find the standard deviation, we need to know two quantities. Two quantities do we need to find? What two quantities do we need to find? So I've got them highlighted for you now. The two quantities, the sample size, and it's technically called, it is a standard deviation. It's the standard deviation of the population. So usually when we do sigma, sigma is the standard deviation of the whole population of all the data. And sometimes SD is called standard deviation, just sample standard deviation, abbreviated as S sometimes. But sigma is the population standard deviation. Now, there are additional things in this problem, like it does give us mu right here, but this isn't so interesting because this is going to remain mu right there no matter what. So the mean of the sampling distribution is going to remain the same, where the standard deviation is going to get smaller. Now, what do you notice about 4, 49, and 64? Those are all perfect whats. 4, 49, and 64 are all perfect whats. 4, 49, and 64 are all perfect whats. The squares, they're perfect squares, because 4 is 2 squared, 49 is 7 squared, and 64 is 8 squared. So what you really have right here is 4 divided by square root of 4, and the next answer is 4 divided by square root of 49, and the next answer is 4 divided by square root of 64. Can I do them all in my head? I don't know. Well, let's find out. The middle one's a tough one. So 4 divided by square root of 4 is 2, because 4 divided by 2 is 2. 4 divided by square root of 49 is 4 divided by 7. 1/7 is 0.1428. And that means 4/7 times that by 4 is, I think it's going to be... Really? I don't want to cheat on the calculator. 7s are a very interesting number. That much. Oh, I don't want to cheat. Oh, Savannah got it. There it is right there. Yeah, I know what a seventh is. A seventh is 1.1428 because it's very interesting to me that, there you go, and there it is right there. Or 4 divided by 7. Just do it that way. Yeah. Good job, Savannah, right there. 2 decimals. Careful, 2 decimals. And then 4 divided by square root of 64 is 4 divided by 8, which is 0.5. And notice how it's getting smaller each time as it gets bigger, because you're talking about for the small size, the medium size, the large size, which has a sample size of 4, 49, 64. And which distribution would be the most normal? This goes to the central limit theorem again, that as the sample size increases, the distribution gets more normal, and the palettes have the largest sample size. So the palettes, regardless of the underlying distribution, the sampling distribution of the mean approaches normal. As the sample size increases, we should get everything right, and we've done it. It is the palettes, and as the sample size, which one was wrong about this one? As long as the, so it doesn't have to be normal. No worries, Savannah, good job. So remember, no matter the shape of the original data, if we start out with lower n, a smaller n, it'll be less normal. And as we increase the sample size, the distribution becomes more normal and tighter, which is the central limit theorem. So this is what it means by the underlying shape of the distribution. And this is what it's saying, that if the sample size increases, it becomes more normal. You don't have to have normal data. If you do have normal data, then you don't even need a large sample size. Normal data, if the data is pretty normal, the sample size can be 1. And it needs to be pretty normal. Like normal-ish, yes, but you could just say normal. Like I wrote normal-ish. Doesn't have to be perfect, but pretty normal. If it's if it's normal enough, then it'll be normal enough for a sample size of 1. Like it doesn't have to be perfect normal. Like if it's normal-ish, like good enough to use the central limit theorem with 1, good enough to use the central limit theorem with 2. So that's what we mean by this. So normal-ish. Is it normal-ish? Normal enough? Yeah, that's what I mean by normal-ish. But yeah, good stuff. Good questions. We'll just knock them all out. Here, we'll do waiter, waitress now. And thank you, Savannah, so much. Waiter, waitress question 47, 43. This is the famous waiter, waitress question. Waiter. Yeah, I know, right? And so Savannah, you got it, because this one is usually tough for people because it really comes down to a notation thing. And we've been saying this endlessly. We talk here all the time.
Notation, brother.
About that notation, brother. Because this question seems like a huge problem, but the problem with this problem is it doesn't really tell you the steps. And the steps are, we know the steps, first figure out if it's cat or quant. And by cat or quant, we ask this because you're going to be using one of 2 sets of formulas. Since we're looking at the tips of a person, and the tips are how much do they get tipped on average, we're doing the mean. So you're doing the mean for the distribution of the sample mean. And that is what we're going to find. And we've actually already found one part of this. We found mu y bar equals to 8.2. We already found that because we just found the mean, and that's what this is. So we now know the center of the distribution. Sample size here doesn't matter. Can we do the next one? You bet. We'll do that next one right there. You got it. And the standard deviation is the original standard deviation right there, sigma over square root of n, which is 60 parties right here. And once again, we mark all of our notation. All the notation gets marked. Know that this is your sample size. Know that this is your original standard deviation. Knowing the sample sizes here is key, or knowing the notation is key, such as sample size. And so now we're going to find the new standard deviation. The new standard deviation is the standard deviation for the sample mean is equal to here we go. I don't even know. Pop bar. There we go. There we go. The original standard deviation 5.40 over square root of 60 equals 2. A little bit harder one to solve. It's like 0.7 or something. What's up? Good to see you in the chat. You got questions? Oh my gosh. I think my brain's on overload. Somehow I got a really good guess at that. I said about 0.7. That was a very good guess right there. There we go. I'm very proud of myself. 100 points, Brian. If you have questions, drop them in the chat. And so with this right here, we now take this information, we plug it into the applet. We're going to plug the applet in the chat so you can go over there and do the applet and solve some of the problems. Now, you notice we haven't really looked at the problem. We're just finding what we need to know for any problem that wants us to do the sampling distribution of the sample mean or the sampling distribution of the sample proportion. So if you get any sort of these problems right here, remember, start solving what you need to solve for and then use that information where necessary. So here's the applet over here on the side of the screen. We're going to put in the standard deviation of 0.69713 and the mean of 8.2. And then let's see what it says. It now says, estimate the probability they'll make at least 550. Well, if we have 60 parties and we want to make at least 550, that'd be $9.18.33, I think. $9.18.33. Or no, $9.16.66. Let's find out. 550 over 60. Yeah. So that is the amount we want to make over the tables, and it should be 9.16666. There we go. I always try to do it in my head because that way if I see what I expect to see, I know I've typed it in correct the way that it should be. If I see something totally different, then I'm like, what did I do? I did wrong in my head. So round to 4 decimals right here. This is what we need to make on average from these tables. So we go here to our distribution. We say making at least this amount. So we need to find the probability using X. And there we go right there. And does it want 4 decimals? There's the probability. I'm going a little bit quick on this one. Remember, swing to office hours at any time. This one we have done a little bit quick. It's like the grocery store problem we did earlier. Hence I'm gonna go a little quick. And I also have longer videos on it. We're gonna do Savannah's other question coming up here next. Thank you, Savannah. And notice it says the best 5%, like the other one said the worst 10%. So it's the same steps we just did on the grocery store problem earlier. Check out that video in this one, where we're doing the best 5% now. So we want the top 5% of the curve. We're going to put in the probability right here and find the top 5%. Notice how this is on the right side, and this is our average tip from the top 5%. Now remember, this is the average tip, and we're doing this for 60 tables. So we have to multiply it by how many tables to find out how much money we made. And there we go, 2 decimals. We should be right. There we go. Once again, I feel like I went a little quick, but always swing by and ask, or we have longer versions of this problem. This one's a classic. Let's do a standardized test for graduate schools. Test for graduate schools. I only have, here we are. More questions. Standardized test. Let me mark it in the video. Do it. Did that last one in like 5 minutes. Okay. Standardized test for graduate school has a mean of this. Automatically, that means we're talking quantitative data. And a standard deviation of this, well, that's the sigma right there. It is unimodal symmetric, which means normal. That's the two concepts. Unimodal means one bump. It's not skewed though because it's symmetric. That means it's normal. Two characteristics of the normal: unimodal symmetric. A test preparation organization teaches a small class of 9. That's a sample size. And a larger organization teaches classes of 49. That's a larger sample size. Both organizations publish the mean scores of all their classes, complete parts A through C. So with this right here, we are going to be doing 2 different distributions, and let's solve it. Now, once again, don't even look at what they're having you do yet, because you have a lot of the information you need, and you can kind of understand where this problem is going to go. So once again, we get our formula sheet, and we start marking the notation. So with the larger distribution, Savannah, you would expect what to be different? I'm going to start marking everything. For the larger distribution, you would expect what to be different? For the larger distribution, you would expect what to be different? Not the mean. For the larger distribution, here's the small, the standard deviation. Here's the large. So for the small, mu y bar equals to 145. The small, the mean for the small is 145. For the large, mu y bar is equal to 145. For the small, the standard deviation for the data is equal to the original standard deviation of 11 divided by square root of 9, which is going to be 3.66, I believe. We can double check the work here in a moment, but 3.66. We'll check in a moment. Standard deviation of the large is going to be the original standard deviation of 11 divided by square root of 49, which is equal to 1.5714. We'll check our work with the calculator. And 11 divided by square root of 9, which is 3, is that right there? We got that one right. And then 11 divided by 7 is that right there. There we go. Is this making sense right there? The n changes, exactly. And we'll highlight the notation in here again because these are the differing sample sizes here for the large and the small. And it really, I cannot state this enough, that it all boils down to notation. We're trying to find these quantities over here for each of the distributions. Like this is the, what is the mean for the large? What is the mean for the small? What is the standard deviation for the large? What is the standard deviation for the small? And then it boils down to knowing your
notation, brother.
Notation. You got to know the notation and got to be able to solve it out. If you don't know it, these problems get very confusing very fast. But if you know the notation, just plug in numbers. So knowing the notation, it really, I promise, the math is not complicated. It's just understanding what are you doing? What's the point of this? And so this is what we would expect from the schools. I'd expect them both to make a 145 on average. Let's put this over here on the side of the screen. We're going to do this real quick. And let's go right here. And there we go. And screen. So we got our work over there on the side so we can kind of see it. What would you expect the sampling distribution, the mean scores to be for each organization? 145. There it is right there in blue. So both distributions should be approximately normal with a mean of 145. Yep. Yeah, just 145, exactly. C. If either organization has a 156, now this is where it gets interesting. They want to know, they're using the last formula over here. They're using this formula right here, which means we need to take the 156 is y bar. They're saying a sample mean of 156. How likely is that? So we take 156 minus 145 over 3.66, repeating. And then for the other one, we take 156 minus 145 divided by 1.5714. So we're literally finding out how far is this sample mean of 156 from the true mean of the distribution in terms of standard deviations. So now we have to go through and solve each one of these and find out how far they are away. So that is 11 higher. So 11 divided by 3.66 is something like 2 point something. There we go. Oh, it's, oh, should have done that, right? Oh yeah. Is it because, all right, let me double check. I guess it's her, right? Oh, would you look at that? Exactly 3. That was high 2. I did it wrong in my head. 11 divided by 1.5714 is 7.47, and it wants to how many 2 decimal places? There we go, right there. 7 point. There we go. It is more likely, so you notice this one's closer. It's more likely the small group will have it because that's less unusual. C is 136. Oh, it is. Oh, the next one's 136, and then all we do is plug in 136 into the data here, and 136 is going to be below. So 136, 136, and now we resolve this. And it does say below, so we don't put in the negative, I believe. If you put in the negative and you get it wrong, let me know. So that is 9 below. If you're wondering how I got 9, we're doing 136 minus 145. That is just the top of the equation right there. And then we divide this by 3.6 repeating. Now we get something in the twos, 2.45 repeating. So 2.45 repeating right there for the small. And then the larger one is also 9 below. We're solving the top of the equation is 9, negative 9 technically, divided by 1.5714. And that gets 5.73. And which of these is less unusual? It's less unusual for this one. It's like, which of these is less unusual? And it would be the small organization again. As long as we did all the math right. No, we did a math wrong. We did a math wrong. Which math did we do wrong, Savannah? Which we did, oh, man, we were on a roll today. We made no math problems. Demi, good to see you here. Investment website, yeah, definitely. I don't think we've done that one yet. Perfect time to come in and say, let's do that. How do we get that one right? Which math did we math? You got a multiple choice wrong? It's this one right here. Okay. So this one should be, there's 11 higher, right? 11 divided by, good. Oh my gosh, I must have typed wrong. Okay. So typo or something right here should have been 11 divided by 1.574. I'll bring back that formula here. Oops. There it is right here. This is the answer I got wrong. You'll have to review the tape to see what I typed. That's why you always want to take a guess. 156 minus 145 is 11. 11 divided by 1.5714. There it is right there, rounds to 7. So that is the answer right there. That is the formula we solve right here. The sample mean minus the mean of the data divided by the standard deviation right there, which you have to highlight the numbers and know what you're solving. So know which numbers you're using, because if you notice right here, we have the mean, and the sample mean was given to us by the problem. And then we also have the standard deviation, which I'll give that a different highlighting right here. We'll go with a nice orange. Standard deviation is right here. We're solving two different problems, but notice it's different depending on the sample size right there. It gets smaller for larger sample sizes. And then the problem also gives you a sample mean right here to say, what is the probability of seeing the sample mean? And then you plug that into the formula up here. So I can't state this enough that knowing the formulas is the key to solving all of these. Because if you know the formula, you can usually be like, oh, just plug this here, do this here. And if you don't make a math error like me, you should be good. And then on the bottom goes the standard deviation, which is found earlier. If you notice two components of this, the yellow or the blue and the orange are found, that literally I clicked the blue. There you go right there. Are found in the other parts. So know how to do these, know the notation. Demi, 100 points for being here. Let's do the investment website question. Okay, we only got 2 more technically. One of the 2 we haven't done yet. Then we have waste. Is it on this one? Have we already done the investment? We can still do it. I need to redo it. Is it on this chat? Is it on the homework, Demi? If it's on the homework, we'll switch to homework right here. Is it on the other set of the chapter, or is it homework? It's chapter 13? Okay, let's go do chapter 13. Wrong button. Chapter 13. Let's do it. Is it homework or quiz? Homework or quiz, chapter 13. Homework or quiz. My coffee's almost done. I got like a Cobra or something today. They said, I don't even know what. They're like, I need something creamy, not too sweet with caffeine. They said, oh, Cobra. I said, does that have caffeine? They said, it's Cobra. I said, okay. I don't know what that is. Tastes all right. Tasted good. Thank you, Starbucks. Like, I don't know. I think I found it. Sometimes I feel old. I don't know all the fancy words. Fancy pants words in there. Okay. An investment. Let's practice those steps. Here we go. An investment website can tell what devices are used to access their sites. The site managers wonder whether they should enhance the facilities for trading via smartphones so they can estimate the proportions. So they want to estimate the proportion of users who access the site that way. They draw a random sample of 210 investors from their customers. Suppose that the true proportion of smartphone users is this. Now here's the thing. We only have one bit of notation given so far, but we can actually get two things from it. Oh no, actually we have two things of notation. We actually have everything we need. Mark your
notation, brother.
What notation do we have, Demi? What notation? Does anyone know any of the notation? Don't even read their question yet. Always mark your notation after you figure out what you're doing. So what notation do we have? Have your formula sheet printed beside you. I mean it. Please do it. Someone did it. They're going to ace the test. Maybe, I hope. What do we have notation-wise? We're dealing with, do people have cell phones? First thing you ask is cat or quant. Some cool color change pens. And do people have a cell phone is cat. So since we're doing cat, we're doing proportions. And we have sample size right here. Sample size is going to be the 210. And we have something else too. Demi, good work right there. We have something else. Once again, we're going to do the question. We're doing it basically right now, but we're marking all of our notation first. Like we're just trying to learn for the test, to be like, I'm going to be ready for the test. Because you can do all the MyPearson problems and not understand what you're doing. True proportion, yeah. And true proportion is P. And as soon as we find P, what else do we find? If we know P, which P is equal to, if you know P, what do you find right after that? If you know P, well, then we know this. That's been found. We know Q. Demi, you're doing great. 100 points, Demi. Keep it up. And so Q is equal to 1 minus P. So Q is equal to 1 minus 0.33. And so Q is equal to 0.67. And for and Demi knows right there, once you've done this a lot, you can do it really quickly. You're just like, well, Q is 1 minus P. And you just know it because you've done it a billion times. And that's really how to get good at this, is to be like, well, they are complements of each other, practicing terms like that. Now notice we know the standard deviation of the distribution, which the standard deviation is just be plugging the stuff into the formula. P times Q over N square root, quote 191. P times Q over N square root, quote 191. 181, we'll find out the hard way. There it is, P times Q over N square root. And we go right here, P times Q. Now be careful when I say over N, and then it's quantity square root, or if you type something in the wrong way, it'll do that to you. P times Q over N square root. There we go, about 3%. And so we've solved this out right here, 0.03244. And there it is. And then even going back and highlighting your notation to practice and know what you're trying to solve and knowing what you're getting where. We actually have all the answers we need. Look at how much we've solved for right here, because this is the standard deviation, and this is the standard deviation of the sampling proportion, the sample proportion. So we have a ton of stuff solved right here. Let's go see what the problem wants us to do with this. We'll put it over here on the side of the screen so we can take a look at it while we're doing it and use all this good stuff we filled out right here. So we're going to use our information to answer the questions now that we've practiced our notation and know what we're doing. Now, if we meet all the conditions, which is random 10% and success failure, we will have a normal distribution. Now, you have to meet all three conditions. Random, your data is taken randomly, which the problem said. Less than 10% of the population is sampled. Your sample size n, lowercase n, is less than 10% of the total. And then the last one is you have at least 10 successes, at least 10 failures. Demi, if 33% of your friends are from New York, so if 33% of your friends are from New York, and Demi, you're super popular, you got 1,000 friends, how many of them would you expect to be from New York? You talk to 1,000 of your friends. You got, this is just a sample size of 1,000. You've got like 100,000 friends, apparently. Less than 10% of your been sampled. How many would you, yeah, exactly. So you just did actually here n times p, which is equal to 330, and then n times q is the proportion we expect, or the amount we expect to not be from New York, which would be this. Now, these aren't our exact numbers right here, really. I did the eraser. For ours, we have to plug in NP and NQ. NP is greater than or equal to 10, and this is going to be the smaller one's the only one you need to check, because if it passes, the other one passes. This is 210, right? There you go. That's n times 0.33 is equal to 0.66, 69.33, I think. There we go. Check the answer. And there we go. There we go. We're good. And the other one will be good too, because we have at least 10 successes for the smaller one. So can I do this one in my head? I'm trying to have some mental math fun today. So the other one should be 0.7, 147. There we go, I think. Which are both greater than or equal to 10. They both have to be greater than or equal to 10. Awesome. Can't find my... Great job, Demi. Thank you so much. Demi confirms the answer right there. And why are we good, Demi? Because we have at least how many successes? At least how many failures? So we have at least how many successes shown right here. This is good right here. And at least how many failures? At least 10, which means it will be normal. Like the distribution of the sample proportion will be normal by meeting the conditions. You're good. Check answer. Good to go. What will be the mean? Well, we found that. It's just up here. Make this smaller on this side. We literally wrote out the mean for the distribution of the sample proportion is equal to the true proportion, which is that. We already found 0.33. So the answer is 0.33. That's the mean. Because it's asking what is this value? And that value, the mean for the distribution of the sample proportion is equal to P. We already know what P is. What is the standard deviation? It's asking this value right here, the standard deviation for the sample proportion. See, it says, what is the standard deviation of the sampling distribution? The standard deviation of the sample proportion. And we found that right there. We already found it, because we could kind of guess where this problem's going. Make sure to do the proper decimals. There we go. And that's it. Good. It's a very good question. Covers a lot of the notation, covers the conditions, make sure to write them out. That's why I always want to say, like, well, what does this mean? Meeting the conditions means that it should be unimodal symmetric normal. Unimodal symmetric is normal. But really good question here. Knowing your notation, knowing how to mark it all. If you go back right here and you start marking the sample size with coloring it, and just knowing how to check each one of these, especially the third condition. So marked the extra 0 in there. Does that make more sense, Demi? Well, so the way it reads, let me read this. You said the true proportion is the mean. Basically, yes. The true proportion is the mean for the distribution of the sample proportion. So this does not say mu equals P. That is not true. Does it make sense, Demi? We're not saying mu equals P. That's not true. Mu is not equal to P. The mean for the distribution of the sample proportion. That doesn't say the mean is equal to this. It says, so that says the mean for the distribution of the sample proportion. Another way is you can take out mu and just say expected. So it might make more sense if you just call this the expected. So now let's think of it this way. If you know that 50% of your friends own a pet, and you talk to 30 of them, so you know 50% of your friends own a pet. What did I just tell you in notation? Like, you know, you've got hundreds of friends. You know 50% of them own pets. What did I just tell you in notation on this screen? You know 50% own pets. Like you somehow know this. It's a fact. What did I just tell you in notation? You know 50% own a pet. You know 50% of them own a pet. So what did I tell you? P hat? Did I tell you mu? Did I tell you n? Did I tell you q? Did I tell you p? Did I tell you SDP hat? You know 50% own a pet. It's a fact that 50% own a pet. So what notation thing did I tell you? Yes, you are technically correct. If someone were to say, I know 50% of my friends own a pet, they're basically saying it is a fact. I do not understand the color change pen sometimes. It is a fact that 50% own a pet. Does that make sense? That's what we've stated. It is the truth that 50% own a pet. It's a fact. That's not from a sample. That's a fact. Now, if you were to talk to 20 of your friends, what percent of them would you expect to own a pet? Not how many, I almost said how many, but if you were to talk to 20 of them, what percent of them would you expect to own a pet? From a sample, what would be the expected sample proportion to own a pet? 50%. What if you talk to 30 friends? What percent of them would you expect to own a pet? I know I'm asking you to repeat yourself, but notice how the only thing in this equation is P. If I talk to 30 friends at random, I'd expect 50%. So that's why it's called the expected sample proportion. So that's saying if you took a sample of 30 friends, you would expect 50% of them to own a pet because 50% own a pet for all of them. So not saying you will get 50%, you would just expect that. You'd expect to see something close to that. And when you draw the sampling distribution, what you'll get is the center of the distribution will look like this, and 50% will be at the center, and then you'll get some sort of variation around it where you might see what is unusual. Does that make sense? You'll say, well, I'd expect 50%. I might not see exactly that, but 50% is at the center of the distribution, and then there's variation around that. So that's what we mean by the expected sample proportion. We expect to see the truth. You might not see it. There's variation around that. So instead of calling it mu p hat, we should probably just call it expected p hat, which is what we mean by that. It's not saying that the mean is equal to p. It's saying the mean for the sample proportion, or over the long run trials of getting sample proportions, we would expect to see this. It's so theoretical. This is a good chapter. It's not one of my favorites and most applied chapters in statistics. So to answer the question, you don't have to find it. You're expecting 50% of people, of 30 people, to have pets. Well, no, you're checking the what right there, Demi. 15 is a good answer. 15 would check the what. You are correct. You actually just did a check on the what right there. By doing 15, you just did a check on the what. That is another thing to answer. But by doing 15, the success, failure, Demi, you're right, 100. Demi, I'm throwing you. We've been throwing some 500 points during office hours. You literally, no, I like it. I don't care. As long as someone says kind things here, we're throwing you 500 points anyways. I was giving you 500 points anyways. Because, and this applet actually shows it, that if you have 30 friends that you're sampling and you have 50% own a pet, it actually shows you would expect 15 right here. So notice this says E for expected amount, which is the mean of the distribution. This one doesn't show it as a proportion. It actually shows 15% here at the center of the distribution. And then notice how it's normal. So if you have at least 10 successes, at least 10 failures, then you will see the normal distribution. Now, if you go here and you say, I talked to 100 friends and only 2% of them own pets, notice that this is right skewed because you'd only expect two of them out of the 100 to own pets. You expect 98 to not own pets. The percent we expect remains the same, but the amount of expected and failures would differ. Now you only have an expected amount of 0.4, which is decimals and way smaller than 10. And notice we don't have normally distributed data. So if you have at least 10 successes, at least 10 failures from data that is randomly collected, and less than 10% of the population, the distribution will be normal. So that is the conditions, the three conditions for the sampling distribution of the sample proportion. Does it make sense, Demi? Really good stuff right here. Notice, watch this. As I make the sample size larger, notice how it becomes more normal. That's the central limit theorem. Because I know what's going to happen here due to theory that if I have at least 10 successes, at least 10 failures, which now we have 40 successes and 1,960 failures. So I'm just subtracting out of the 22,000. It's like 2% of lottery tickets for a contest are winners. How many winners would you expect? 40. And then losing probability is 98%. And then you times that by 2,000. But these numbers right here have to add up to 2,000 because this is expected winners and expected losers, which is NP, NQ. Because if we say, we know for a fact we have 2% winners. No, well, great job right there, Demi. Yeah, well, it's kind of chill time right now. Maybe I'll do the rest of the homework. I know people watch the videos later. I'm like, I should do a little more work here. I could finish up the homework. Finish up the homework. See here. We did this one. We already did all the homework. If you're watching this right now, you might check out the last. We already did this one. We did all these last time. We've almost done every problem. As the sample size increases, the mean will stay the same. Mean doesn't change. Standard deviation gets smaller, it gets more normal. As sample size increases, standard deviation will get smaller. That's the central limit theorem. Suppose, what proportion would you expect to see? That's the true proportion. If 30% of people talk on their cell phone, I expect to see 30%. According to Pew Research, 26.6% are pessimistic about the future. Is it real procedure to use a normal model? Yeah, you meet the conditions, because 26%, you have way more than 10. As long as it's random, less than 10% of the population, and we do have at least 10. There are more than, yeah, and it times that by 10 to find out less than 10%. They have at least, no, we don't want less than, you want at least 10 failures. Her sample size is small right here. She has 30 sample size and 7% go on spring break. You'd have way less than 10 expected successes. You'd only have 2.1 expected successes. So you don't meet the success failure condition. This has nothing to do with nearly normal. That is for quantitative data. Looking at the histograms would be the smallest size. Don't even look at the histograms because as we increase right here, if you have a success rate of 8%, well, if you have 100 sample, you wouldn't have at least 10 successes. You have a sample size of 200, have at least 10 successes. Failures would be 184. Notice how it's just success failure condition right there. What's the success failure condition state? You have at least 10 successes, at least 10 failures, so it would be normal. I just saw at least. Nope. I should have done slower. Or at least 10%, so it's met. Yeah. There we go. What is? Yeah, no one at least. As long as you have at least 10 successes, at least. I'm doing it during the song. This is the way the data looks, so we can't use the empirical rule because the data has already been put into the sampling distribution. So it's not unimodal and symmetric. It's right skewed. We can't really use it. It's right skewed. So the central limit theorem, or not the central limit theorem, the empirical rule would not apply. It's based for normal data. Just can't do that right there. Can't use it on that data. What is this right here? So this is, what does p hat mean? That is the sample proportion. The amount out of the sample. Oh my gosh, I'm reading too quick. Meaning this is that sample change reported. Yeah, sample change reported. It's the best guess at the truth. There we go. It's not the best guess at the proportion because at the sample, we know what the sample is. The standard error is going to be calculated here from p hat. I go through these way more slow. I'm just trying to see if I can speed room. Calculated using p times q over n square root, but we don't have p, so we use p hat. There it is right there. Check out Friday's video where I go a lot slower. I'm just relaxing here doing work. And so what is this? That's the estimate of the true standard deviation. So the standard error is the best estimate of the standard is the best estimate of standard deviation, sample distribution, which measures the amount of variation in the sample and the population portion. Yeah, it has to have a sample size related to it. That question is okay-ish. Really? I lost that one? And this one just shows that it gets more normal and tighter. This one can take a moment. Let's see how quickly we can do it. Let's say here, we'll speed run it. Go Hacker Man on this. Then we'll maybe do something else. Who knows? But we got a lot done during this. I'll put this, well, this is a secret if anyone finds it. Check out the other video where I go a lot slower. What is the shape? So I'll briefly explain, because if anyone's watching this, I want you to know what I'm doing. The central limit theorem states two things. The distribution will become more normal and tighter as the sample size increases. take a look right here, and what you'll see is the sample size going from 20 to 50 to 75 to 100. Now, I wish they showed you this visually, like I know it's visual here, but I wish they showed you with something like this, where we're talking about a sampling distribution where we have two observations being taken from the top right here. Now, there's the mean of it. Now, here's another two, and there's the mean there. Now, here is what happens if you do this tons of times, which is what they're doing. You get something that looks like this. Now, this may not look more normal, but it is because that was left skewed, and it's trying to get a mode in here and a second modal area. It's a little bit bimodal right now, but it's more normal than original. And it's also tighter. The standard deviation has gotten smaller from 10.52 to 7.44. And I can tell you that if I do square root of 2, I think it's 1.414. There we go. I've known a lot. And if you go 10.52 divided by that, it's going to be about 7.44. There you go. How did I know that? Well, because of this quantity right here is the original standard deviation over the square root of n. Notice that the standard deviation gets smaller as I increase n. So we go up right here, and this is going to be about 2.11. 2.11. There we go, 2.10. I should have said 2.10. Go back to 2.11. There it is right there. And how did I know it was 2.11? I divided this by square root of 25. Square root of 25 is 5. And now it's more normal. These are the two things of the central limit theorem. I keep stating that throughout this video if you've been watching. That the central limit theorem states that the distribution of the samples will be more normal than the original data. And it'll be tighter by a factor of square root of n for quantitative data and p times q over n square root for categorical data right here. Notice the two formulas, and we're really only speaking about this portion, trying to highlight, really. Only really speaking about this right now. Only really delving into this, that this n right here is a divide by, making the standard deviation for either distribution smaller. Now, the mean does not change. The mean is going to stay in the same spot because the mean for the distribution of the sample proportion and the mean for the distribution of the sample mean is equal to the true proportion or the true mean, depending on what kind of data we're working with. So knowing this concept that the mean doesn't change, I don't even need to look at the simulations to know that when we do this, the shape is going to be still skewed, I believe. It's still skewed to the left. And the center is going to be wherever the center was, 0.86 right there. And that's between these numbers. That's the same center because it's going to remain the same. And the sampling distribution has a spread, and we just look at from 0.5 to 1. I'm just literally finding how far is 0.5 from 1 right there. And then we go right here, and that's a spread of greater than 0.4. On the next one right here, you'll notice it's still a little bit left skewed, but what you want to start doing is you want to start checking the success failure condition. The success failure condition says it'll be normal if we have at least 10 successes, at least 10 failures. Check by taking the sample size 50, timesing it by the smaller of n, p, and q. P is 0.86, so q is 0.14. We do not have at least 10 successes. So since we don't have at least 10 successes, it's still going to be left skewed. The center is 0.86, which is between these numbers here, and the spread is going to be 0.35, which 0.35 is contained in these numbers here. No, what did I get wrong? I can't seriously be this one. Sometimes they change the center on me a little bit. Did they shift it? This is why this question is not one of my favorites, because if you be careful, you have to look and see where is this peak, and that's 0.65 to 0.70 to 0.75 to 0.8 to 0.85, 0.8 to 0.85. And technically, the true proportion is expected to be 0.86, or the sampling proportion is expected to still be 0.86, but visually speaking, the way the bins of the histogram came out, 0.8 to 0.85 is where the center is. I'm doing it a little quickly, but make sure to look at it when you're doing it, because that's the way you'll get all the points. The shape of the distribution will now be normal because we have at least 10 successes, at least 10 failures. 75 times the smaller of P and Q is times 0.14 is going to be 10.5, I believe. There it is. With at least 10 successes, at least 10 failures, it'll be approximately normal. With the center of the distribution, 0.86 is nicely in that bin. I like that one. That should be right. And then it is going to have about the same spread as the previous one right here. And we'll check the answer. How did I know that spread? Well, I've done it a lot, but notice that this is 0.35 to 1.0 right there. Next, we go right here. The shape of the distribution is still, it's even more normal now with 100, because with 100, it's nice and easy to calculate. Times it by 0.86, you have 86 successes and 14 failures. The sampling distribution is centered at, now this is where it gets scary because these bins overlap. So notice it could be 0.84 to 0.86, or it could be 0.86 to 0.88. We're not going to be getting this wrong, so we're going to go look at it. We have to zoom in. This is 0.75 to oh man, I hate this. That is where, okay, so that is 80, 85. Oh, 85 is in the center of the bin. And then this is 90, 95. So we have to look for the bin that contains 85, because this peak right here contains 85. So whatever bin contains 85 is the answer. That bin contains 85, it's good. Once again, if you're wondering how I did that, you have to know how to look at the graphic and take a look right here, where that's 75, 80, 85, 90, 95, just dividing into equal parts. A few people are still probably wondering how I did this, so I'm just going to draw it for you so you can see. You have to go right here and say this is 80, 85, 90, and 95. And that would mean 85 is in the bin where the peak is at, making it the 84 to 86 bin. Might be hard to like, well, where exactly is it? We just know 85 is in the bin. This is the only bin that has 85. Now it's a little more tighter. It's more tighter, so it's going to be there between 10 to 25, and that's right here. It's 20, the range from 75 to 95. Got it. Good to go. Good question. Well, we've done all of 13 and 14. Done all of it. Someone texted me. Who knows? What did they want? I don't know. Gotta turn off Pokemon. Oh man. My dentist wants to know how we did. I haven't seen it properly. It's like, I think because they said like this is a so-and-so name, and then my dentist called cosmetic. Yeah, y'all know where I go to the dentist. But my phone was like, "Do you want to change this to this name?" I'm like, "No, it's labeled properly, phone. I have it named that for a reason. Just because the person said hi, it's so-and-so from this, I don't need it renamed. I need it properly named." Well, we've done a lot of work during this office hours. Might take a little bit of a break here. Got the test coming up, and yeah, really proud of people. With that, gonna head off. Bye for now, everyone. Bye.